ready to run to running, yes, this is a valid transition because of dispatching. Now, is it possible to move a process from waiting state or from IO wait to running? Is it possible for a process which is in IO wait to make it to ready to run? Is it possible to make a transition from IO wait to terminate? Okay. Now, ready to run to running is a valid transition. Remember, whenever this IO event elapses, no process will directly go to again running. Why? Because as I have told you in multi-programming, there are more number of jobs running in a they are loaded into the memory, and only one process will be running on CPU if you are talking about uniprocessor system. So if this process exits, okay, then scheduler will take any one of this process and bring that process into running state. If a process is performing some IO operation, this process will be busy in IO operation, and some other process will be taken by the scheduler, and it will be in running state. So no process from IO state will be moving towards running. This is not allowed. So this transition is not allowed. IO wait to running is not allowed. Okay, we have one more combination. Is it possible to have from running to ready to run? Okay. So from ready to run to running is allowed, and from IO wait to running is not allowed. But IO wait to ready to run, yes, this is a valid transition. When IO event occurs, then always process moves from wait state to ready to run state. Okay. Then comes IO wait to terminate. Is it possible for a process only in case of abort? It happens, but generally when you talk about state transition diagram, it's not a valid transition. Okay. If this process want to terminate, then first it has to move from ready to run, and from ready to run it has to come to running, and from it has to be exited. Okay. Now this is actually a state transition diagram for multi-programming system. Okay. And this multi-programming which doesn't support preemption. So if there is this transition, this is invalid transition for multi-programming system with no preemption. With no preemption. Okay. And this is a valid transition if you have multi-programming with preemption. Now this becomes a valid transition. Okay. This generally happens called timeout, as we discussed in time sharing system, which is actually a multi-programming with preemption. So this transition is valid for time sharing systems or multi-programming with preemption. Now there is ever possibility that now what do you mean by ready to run? Actually there are many number of processes which are on a system, which are loaded into the memory, and they want themselves to be scheduled on system. So but any one of them will be selected by the scheduler. So now how this scheduler will keep track of which process will be taken next. Okay. So in order to make this decision easy for the scheduler, operating system maintains few queues. Okay. Actually there are two types of queues which are maintained by the operating system. One is called device queue and another is called ready queue. Now what do you mean by device queue? In device queue, all set of processes which are waiting for run, which are ready to run, as I have told you, all the processes whose state is ready to run, okay, will be waiting in ready queue, and all the processes which are waiting for some IO operation. There is ever possibility that in multi-processing, in multi-programming, where n number of processes are waiting for their turn, it is possible that more than two processors was opting for same device for IO. So in that situation, we need an IO queue which will queue up all these processes which are waiting for their IO. So it is possible in multi-programming system that more than two processes will be in same state. Okay. So if there are 10 processes, it is possible that 5 processes in ready to run state, 2 processes in IO wait state. So how these processes will be queued up? Okay, they will be queued up with the help of different queues, ready queue and device queues. So ready queue will contain all the process in trees which are ready to run, and device queue will keep track of all those processes which are ready for which want to perform some IO operation. Right. Now, what do you mean by process is in queue? What do you mean by process in queue? Process in queue means actually the process control block will be in queue. As I've told you that the designer of the operating system thought that PC they discussed this. They defined the operating system as a data structure, and it has attributes. So all the attributes are contained in PCB. So that PCB will be in queue. So process is in queue. It means the process control block is in queue. Okay. So now what is the data structure which is used? Now it depends upon different algorithms. If you are using first come first serve algorithm, then this ready queue will be treated as queue. And if it is some other algorithm like round robin, or if you take it as priority scheduling algorithm, then it may work as circular queue, or it may be implemented as a single linked list. Okay, so depending upon the algorithm type, the implementation of these queues happens. So this is very important transition. If a process is running, and the transition is possible from running to ready to run only in multi-programming with preemption. Okay. So now there is ever possibility that this is very interesting. Suppose as I have told you that queues are of two types. One is ready queue and another is device queues, right? So ready queue will keep track of all the processes which are ready to run, and this will keep track of all IO operations. Okay. Now what happens, suppose the size of this queue is to accommodate n processes, but there is possibility that more than n processes are in ready to run state, which is exceeding the capacity of this queue overflow, right? So in that situation, what operating system will do is, this operating system will take few of the processes which are ready to run and suspend them, meaning it will take and put into the secondary storage, a special area in secondary storage called swap area, wherein or in disk, all these processes PCBs will be copied. Okay, this is called suspended, ready to run, suspended, ready to run, suspended. Okay. Now again, if there is a provision to accommodate any ready to run process, then again what happens? Those PCBs can be brought back again. Now similarly happens, there will be more number of processes which are in waiting queue, then again they go to secondary storage, and again they may back when there is a provision to accommodate all of them. Okay. So among this all these states, when you are seeing running, ready to run, processing, this is the state of the process while they are in execution. They are in main memory, and these two states, suspended ready and suspended for IO, they are in secondary storage, but still they are called as processes, suspended processes. So that's what it is. Now, there is one more important thing which we should be aware of, is that, now I'll just draw this diagram. Suppose I have a disk here, and I want to load these programs, then it comes into ready queue, right? These are all ready queues. These are the PCBs ready. It's ready queue. Then this process, here you will have CPU. Okay. Now from ready queue, the process will be selected randomly according to the scheduling algorithm, and it will be given to process. CPU. Now CPU will execute the process I, and if it turns to completion, it terminates. Or otherwise, what happens? It may again give it back to ready queue, or if it is performing some IO operation, then it will give it to device queue, So this is a device queue. Now from device queue again, yeah, it will be allocated to CPU. So or if it is waiting for some event, okay, then you suppose you have some event queue. Okay. So in a system you can have multiple queues, okay, and each and every queue is keeping track of different processes which are in different states. If a process is in IO state, then we have a IO queue. If a process is ready to run, then we have a ready to run queue. Then there is actually who is doing this? Who is taking from disk a program and loading into memory? Now here comes different types of schedulers. Actually, long-term scheduler is responsible for taking program from disk and bringing it to ready to run queue. So generally, long-term scheduler is responsible for increasing the degree of multi-programming. If there are more number of processes loaded into the memory, then the degree of multi-programming will be more.